I'm going to be talking to you today about model evaluation, hopefully try and sort of stimulate some thoughts from you all about how you go about assessing whether the models that you're using are appropriate or not. And in particular, perhaps moving away from the idea that if you want to evaluate the model, all you need to do is think, well, I've got a model, I want to model X, let's do an experiment of X, and then look at the model results and do a comparison. There's a lot more to it than that. So the way I'll do this is by going through this model evaluation protocol that Olaf has already mentioned this morning, that we've put together for evaluating LNG dispersion models. I'll then talk about some applications of this MEP. In fact, you've already seen some of it this morning. Then we'll go on to talk about evaluation of source term models that provide an input to these dispersion models. Okay, so the model evaluation protocol. I'll start off by going through the physics of accidental releases of LNG. And as you'll see that this is key to developing this model evaluation protocol. So you'll see how by going through the spread and vaporization of spills of liquefied natural gas, that will feed directly into the development of this model evaluation protocol. Okay, so accidental releases of LNG. An accidental release can be conveniently split into two main parts in terms of when you're trying to model it. First of all, the source term, which is basically the spread of the liquid, the spreading and vaporization of a pool of LNG, and then the vapor dispersion. So you've got two very different types of physics going on here, and it makes it very convenient to model them separately and use different models. So the majority of what I'm going to talk about today is going to be on the dispersion. Okay, LNG vapor dispersion. Now this is characterized by dispersion of a dense gas. It's dense because it's cold. And the main factors that will affect the dispersion of this gas are the atmospheric stability, the presence of obstacles, terrain, and the wind speed and things like that. So this is fundamental to understanding what process we need to go through to evaluate an LNG dispersion model. Okay, now model evaluation is quite a dry subject, so I've just put a few movies in here to try and make sure everyone's still awake. Now this isn't, this might run a little bit slow. This isn't LNG dispersion, but this is actually the dispersion resulting from the incident at Buncefield a few years back. So this just highlights the effects of, well, in this case there was no wind, but also obstacles and the slope. You can see there's very different propagation rates in different directions depending on where the obstacles were, which way the ground was sloping, and so on. So it's very important that we understand what these key physical effects are that affect the dispersion. Okay, so the motivation for this work, and as I say, you've already heard some of this already this morning. In the US, they've got a very sort of prescriptive approach to assessing safety on these LNG terminals, LNG sites. They state that the flammable cloud from a given specified release, what they call a design spill, should not go over the site boundary. So then the question came up was, well, how do you assess whether the model that you're using to demonstrate this, how do you assess whether it's accurate or not? Previously, before we did this work, their guidance basically said you have to use Degadis or FEM3A, and other people were saying, well, we've got models, we know they're better, well, why can't we use those? Okay, so the starting point for our evaluation protocol, we didn't start from scratch. We started by looking at two European projects that had previously been carried out on model evaluation. The first one is this model evaluation group. They put together some sort of fundamental ideas in terms of model evaluation, particularly looking at sort of consequence models. The result of that European project was they put together these two quite small pamphlets that very concisely describe the key processes you need to go through in terms of evaluating a model. I'd highly recommend people have a look at that. They're very, very useful. This was then followed by the SMEDIS project, which then looked more specifically at dense gas dispersion models. It wasn't just LNG, but dispersion of a whole range of gases was of interest there, chlorine and all sorts of things. I think one of the things that project did highlight was how difficult a process it is really to fully evaluate a model. I understand during the project itself they were going to go through a process of evaluating something like 30 odd models and only got through about half of them within the project. So it's a big time-consuming process. Okay, so what does the model evaluation protocol look like? Well, it's based on three key areas. The first one is the scientific assessment. So this is looking at the physics of LNG dispersion, saying what are the key physics of that dispersion that need to be encapsulated by the model. The next part is verification of the model. I mean, this is something that's usually done in-house, so it's testing whether the equations are appropriately solved by the software, making sure the implementation of the model in software is working as it's intended. And the final part is validation, which we've seen a lot about already. People talk about verification, validation in terms of solving the equations right and solving the right equations. It's one sort of simple way of looking at the difference between those. Now, we're not going to talk about verification anymore. We quickly found that this is quite a difficult thing to address for a model that you're not developing yourself. So to a significant degree, I think you need to rely on the verification that's been done by the model developer. So how do you go about applying this model evaluation protocol? Well, we put together a structure for this. And it starts off with a questionnaire that extracts all of the relevant information that you need to carry out the evaluation of the model. We then put together qualitative evaluation criteria. So this is mainly based on scientific assessment, saying what are the key things that need to be embodied within the model to model this LNG dispersion. We then actually created this validation database, pulled together lots of different data sets and said, these are the experiments that you need to model to validate your model. And then the next step was, even more challenging, was actually to say how accurate is accurate enough. So we put together quantitative evaluation criteria to say how good agreement do you need to get to say that this is an appropriate model. And then we put together a template for a model evaluation report, which basically reports the whole of the process of this evaluation. Okay, so the scientific assessment, I mean, I'm not going to go through all of these in detail, but basically these are the qualitative assessment criteria that the model needs to meet to get through the model evaluation protocol. So it's the key things like takes into account the effect of wind speed, takes account of the effect of atmospheric stability. Now, there's some things that will have an effect on the ability of a model to represent vapor dispersion that aren't totally necessary to be used in practice. So we didn't want to exclude any particular class of model. So, for example, integral models clearly aren't generally applicable for cases where you've got obstacles and so on, and varying terrain. So what we did in terms for the validation database, we split up the database into two groups for obstructed cases and unobstructed cases. So you could say, okay, it's valid for this type of scenario, but for not these. So we didn't want to exclude any particular classes of models when we put this protocol together. Okay, so validation. I mean, this is perhaps one of the key things here, really, is what is the purpose of validation? It's basically challenging the model across the full range of the key physics that you're trying to model. So we go back to these scientific criteria. So your model's got to be able to represent all of this physics. So how do we go about putting together a validation program that challenges the model across that full range of physics? Now, that's not simple, and you're not going to do it with just a small number of experiments. Another way of looking at validation, and perhaps just demonstrating how broad it really needs to be, is it's almost impossible, I would say, to validate a model. What you're really doing is it's a failure to demonstrate that the model is invalid for a particular case. So really, when you're validating it, all you're saying is, in that case, it works fine. But what about outside of that? And that's really where the scientific criteria come in. Without those scientific assessment criteria, if you don't meet those, then there's no way you can say that the model is going to be appropriate outside of the bounds of the validation cases that you've looked at. Okay, so in terms of putting together a database for the validation, so as I say, the data's got to exercise the model's ability to account for these key physics in the dispersion of the LNG. The test conditions need to be well specified. Averaging time to data must be known. I mean, perhaps it sounds trivial, but that's of vital importance. That information is known. For wind tunnel scale data, the scaling factors need to be reasonable. The source term is of particular importance, so having that well characterised is vital. By modelling, I'm aware that by modelling a source in different ways, you can get completely different answers. And in fact, I know from the experiments, people who've done experiments in wind tunnels, they've said that by setting up the source in different ways, again, it has a very significant effect on the resulting dispersion. Measurement uncertainty should be low, and the data should be available. Again, it's not always the case for the experiments that have been done.
What do you mean by wind tunnel scale is acceptable? So you're accepting wind tunnel data?
Yeah, that's right. I'll perhaps come on to that a bit more in a minute. So once you've specified the experiments that you want to model, then you come up with these key issues here. You've got to actually work out what the physical comparison parameters are. That basically means what measurements are you going to compare the model against. So is it temperature, concentration, cloud width, or so on. So you've got to work out what these parameters are. Once you've worked out what parameters you're comparing, then you've got to look at how are you going to compare the experimental data against the model. So that's the statistical performance measures. And again, Olaf has already mentioned those this morning. Then finally, once you've got a means for comparing your experiment to the model, how do you say the model is good enough? So that's where the quantitative assessment criteria come in. And I think I've got another video here, so make sure you're awake. This is one of the Thorney Island trials. This is a instantaneous release of Freon, I believe, and some other tracer for the measurements. So this is one of the validation cases that's in the database. A very important data set. Okay, so the physical comparison parameters. So we've developed these based on previous research in this area. So we're basically using the maximum concentration at a given distance from the source, and also the cloud width. And the final one is also looking at some point-wise comparisons of concentration. There's less of an established sort of field of data on these point-wise comparison parameters. So so that makes it harder for us to say what level of agreement is satisfactory. Okay, so before I sort of talk about these quantitative assessment criteria in more detail, it's interesting to think about what sort of level of agreement should you be expecting. Now, in this paper by Davies, he showed looking at some wind tunnel data for two nominally identical experiments. He was getting differences in concentrations downstream of the source, and they were varying by an order of a factor of 2. So ideally, you'd do all of your model comparisons against ensemble averaged experimental data, but that's very rarely available, particularly for field trials. So you need to bear that in mind. And it also means that if you do see model predictions against some experiments and you get the model predictions going through all the points, it does make you think, well, they're either very lucky or they've been fiddling their numbers. Okay, so the quantitative assessment criteria. Now, I haven't got the definitions of these here. If you were watching carefully earlier from Olaf's presentation, he had them up there. I forgot to include them in my presentation. So these criteria are that the mean bias has got to be within 50% of the mean. So that basically means if you average across all of your experimental data, on average, you should be within a factor of 50%. And that basically corresponds to this mean relative bias being between these values and the geometric mean being between these values. I can just suggest that I can provide you with what these terms actually mean if you're interested. The second factor is looking at the scatter about the mean. So even if on average you're correct, how are your points scattered about that mean? So there we've got two criteria that measure the scatter of the measurements against the mean.
Is that within one measurement, or is that between the measurements, the scatter?
Yeah, that's if you plot all of your different measurements out on a graph or something like that. It's how they are spread around the mean. The third one, which is perhaps the easiest one to get your head around, is looking at each individual measurement compared to the model prediction and saying that at least half of those have to be within a factor of 2 of the prediction. So these quantitative assessment factors were based mainly on research that's been done by Steve Hanna in the past. So we had quite a good basis for knowing, based on previous evaluations that have been carried out, what a reasonable model should look like. Okay, so these are the tests that form the validation database. So here we've got some large-scale LNG trials mapped in Sainsbury, Coyote and Falcon. A range of different atmospheric stability conditions. I mean, most of the data is for either neutral or unstable conditions, but we do have some in stable conditions as well. Here, so those were, well, actually, the Falcon trials there, I think one of those, if not a number of those, were for obstructed releases. The rest are for unobstructed releases. Then we've got the Thorney Island trials, which I showed you the video of, and then a number of wind tunnel trials. There you've got a greater flexibility in looking at different obstructions to the vapour dispersion, so you can challenge the model in different ways. Okay, so all of that model evaluation protocol and also the guide that tells you exactly what's in the database is available in these two publications, which you can download off the web. The database itself, I think you can just ask for it from NFPA or myself or anyone else that's got a copy, I guess. So, well, the outcome of that work then basically got included into the NFPA standard. So it is now part of their standard that this MEP, model evaluation protocol, has to be used in your siting for your LNG site. So then that takes us nicely on then to application of the MEP. So Olaf has already talked about this already. So Gexcon were the first people to apply the MEP in detail. It was written up in this comprehensive paper in the Journal of Loss Prevention. And we spotted that just last month you put this on your website saying that the FLACS is now approved for use in the US for LNG vapour dispersion. We've also been doing some applying this MEP at HSL. We've been using two models, Drift and Crunch. So we've been going through a similar process. We keep being on the verge of being able to publish something on Drift, and they brought a new version out, so we go back and start again. But we've now basically gone through this process and going to be writing that up soon. So overall, I'm not going to go through the details, but overall Drift gets pretty good agreement. So what you get when you run through this process, you get tables like this that demonstrate what these statistical performance measures, what values you get, and you can compare them to the acceptable range. Another way of presenting all of this information, now this is one of these graphs that's, once you've got your head around it, it tells you a huge amount of information. Basically this compares the geometric mean bias along the bottom and geometric variance along the top. So the ideal result will be something down here with a geometric mean of 1, a variance of 0. So if your geometric mean is about 1, that means on average across all your simulations you're doing well. But if you're up here somewhere, you get it's quite a large scatter between how far apart individual measurements are from the experiment. So this case, for example, on average, if you average it across all the experiments, it does very well. But if you look at individual measurements, there's a large scatter. So individual measurements are quite some way off the data. So in terms of this factor 2 correlation, only 22% of individual measurements are within a factor of 2 of the experimental data. Okay, so I'm very briefly going to talk about source terms. Source terms is a much harder subject to address because there's so much more uncertainty in what's actually going to happen when you get a release of LNG. You might have, there might be a catastrophic vessel failure, you might get a jet release at a height, so it all vaporizes before it hits the ground, you might get a pull spread, there might be some impingement, there's vapid phase transitions, subsea releases. It's a lot harder to characterize what's going to happen. In practice, most people, when they're modelling this, and certainly most of the experiments are based on having a pull spreading and vaporizing. So most of the work has been done on that subject. So because there's a lot more uncertainty in what's going to happen, and also because it's not such a well-developed area of science, we haven't put together the same level of detailed approach for evaluating source term models. So what we did was we basically put together a best practice guide to assessing these source term models. So again, these this work is all published in these reports, which you can download off the web. This work was jointly funded by NFPA and HSE. So to summarise, I talked about this dispersion model evaluation protocol and how it's based on these 3 key areas of scientific assessment, validation, verification. Just talk very briefly about the implementation of this MEP for FLACS, drift and crunch. And finally, talked about the source term evaluation, which is clearly much more difficult to do. So just finally, I just wanted to make a few acknowledgements. I talked about, gone through very quickly a huge amount of work here. So I just want to acknowledge some of the work from my colleagues there. Now, have I got any questions? Yeah, at the back.
What was the curve, the sort of parabola that was shown on the slide? What was that line representing?
Right, the curve. This one, the vertical lines.
Well, the actual...
Oh, the curve itself. Okay. Well, this is all the model predictions will be inside that curve. It's sort of physically impossible to have a result outside here. It's due to the mathematical relationship between the mean bias and the geometric variance.
That's a 0 variance line.
It's a 0 variance line.
I think can you repeat the questions?
Yeah. There was another question over there.
Are a drift and crunch commercially available, or are they just HSC tools?
Are drift and crunch commercially available? I don't think so. Crunch certainly isn't. I can't imagine anyone wanting to buy it. Is that recorded? Yeah, at the back.
I've been looking for some more statistical analysis of this curve, because I asked the statisticians at our department at the University of Bergen, and they have never heard of it. Do you have some good references, except from the ones from Hannah, that explains the mathematics behind it and so on?
Right, the question is about the mathematics behind this curve. I mean, I'm not a statistician, so I think this is all information that we inherited. We didn't want to start from scratch, so we looked at established approaches, which gave us a huge amount of information on what's a good result and so on. So
it's just that we're working on our own model evaluation protocol, and we planning to adopt most of it. I wanted to have the background so I could write where is it coming from, and I couldn't find it. I just I end up finding HANA 1991 or 2 or something, and then it stops there in a way, and then maybe it hits. But there, I can find what's behind and reasoning and why this is better than anything else.
Well, I'd be surprised if now you couldn't do something better than this. Yeah, this is an approach that's been used for 20 years.
They are doing something a bit similar, different. They are doing a bit more elaborate model evaluation for their higher models and so on. So I wanted to know if I should go all the way over there or stay with this.
I don't know. Yeah, if you've got time, I think it would be well worth revisiting this and saying, is this still the best approach?
This is what we are looking at.
Yeah.
Just a comment on that first. I think it stops at HANA, but you can try sending an email and ask
I
him.
tried that. He doesn't answer.
So I think, and I think it is very good for explosion, this curve. For dispersion, you get a problem with points that are not picked up by the plume, that zero division issue.
Yeah.
So I think it's better for explosion, like for blast and fire project, than it is for dispersion actually.
Yeah, I mean, so there was about 5 different criteria that we used, and different criteria have got advantages and disadvantages in different cases. Some where you're measuring 0 and they can skew the results one way or the other. So I think you're always going to need different parameters to compare.
One question on the different experiments. You mentioned that somebody did wind tunnel test and they got factor 2 difference typically. When we simulated the Falcon test, we had big problems reproducing those, so we didn't do those very well.
Yeah.
And unfortunately, those were the only large-scale obstructed ones. But we suspected that there could be flashing in the pipes on the way out. And when we did a simulation where we assumed flashing in the pipes for the source, we got reasonable results. Any comments on that? Or?
Yeah, so Olaf was just saying that they had problems with one of the Falcon trials where it looks like there's some uncertainty in what happened with the release conditions and whether there was some flashing in the pipe. I think we did okay with those Falcon trials. I mean, I didn't do this evaluation myself and haven't actually fully read what's been done. But I think that would be well with us comparing notes actually and going through that again together, see what lessons learned there are and whether there's any new data that, if there's any gaps really in this database that need to be addressed. Perhaps with the those tests, the ones you mentioned this morning.
Jackrabbit?
Jackrabbit, yeah.
Yes, the NFPA approval is for software or for a company with a software?
I think it would be the NFPA approval would be for the individual software.
Individual.
Is that right? Yeah.